to join us tonight, we have Dr. David Grinspoon, who is the U.S. scientist for Venus Express, which was a European Space Agency mission, and he's here to tell us what we learned about Venus from Venus Express and what are the remaining questions. So, David, are you with us? Can you join us? There you are.
Good evening.
Hello, David.
Yes.
Nice to see you. So, welcome.
Thanks a lot.
Anyway, so David, first of all, congratulations on all the wonderful successes with Venus Express. What exactly was your role? Can you clarify that for us?
My title is Interdisciplinary Scientist. And that is a really fun role because, you know, on a spacecraft team, there are all these different instrument teams. There's the camera team and the spectrometer team and magnetometer team. And the interdisciplinary scientist is supposed to sort of float amongst all the team and help to, just what it says, promote investigations that kind of go across those disciplinary boundaries. And so it's been a really good experience, both, you know, culturally getting to know all these European colleagues, and then, of course, scientifically, it's just been really incredible.
So tell us about Venus Express. What were some of the questions we had about Venus before it was launched, and what answers, what insights did it provide to us?
Well, first of all, it's called Venus Express. It's kind of a funny name for a spacecraft. It sounds like a delivery service or something, but it has that title because there was an opportunity to send a spacecraft using a spare from the Mars Express spacecraft. Basically, there was another Mars Express that wasn't fully built, and you could propose another spacecraft, and so it had to be done really quickly and really cheaply. But given that, it was an amazing set of instruments, and basically the overall question was, well, it's really about what makes Venus tick. But Venus Express was like our first weather satellite at Venus. You think of the importance of weather satellites on Earth, not just sort of snapshots, but these continuous observations. And this was our first opportunity to really do that at Venus. We'd had spacecraft go there before and do really important things, but not sort of lingering around in orbit for all these years, making these detailed observations of the clouds and the motions of the atmosphere, and looking for lightning, and even being able to image the surface to some extent in this very clever way in the infrared. So it was really the ability to do these continuous observations and get at the complexity of all the changing motions and the very dynamic environment that we have there.
Now, before you tell us what we learned, why do we care about Venus? Why bother going to study it? I mean, what does Venus have to do with us?
Well, personally, for me, I always call Venus my second favorite planet, and that's including the Earth. Because it's a fascinating place because it is in some ways so much like the Earth, and yet in some ways it's so different. It's almost like Earth's alter ego, or as some people have called it, Earth's evil twin. But, you know, it's almost exactly the same in so many ways. It's virtually the same size, same density, so which tells you it's made out of the same stuff. It's very nearby. It's the closest planet physically. And so you might expect it to be very similar. And yet it's evolved in this drastically different direction where it's so hot and so dry. You know, the climate just ended up in this very, very different state. So it's telling us something about the different paths that Earth-like planets can take. And for me, it just presents this huge mystery. You know, how do these planets, which are essentially twins and nearby, end up so drastically different, where Earth is, you know, the way we like it, and Venus is so hot and so dry. And, you know, it's a little unnerving. You know, can this happen? Don't let this happen to your planet.
What is the difference? What happened?
Well, we think what happened is what we call the runaway greenhouse. Everybody knows about the greenhouse effect by now, I think. But picture a planet where the greenhouse effect just gets really out of control in this self-reinforcing way. If you have a planet much like Earth, but it's enough closer to its star so that the sunlight, the starlight is just that much more intense, then you can get this feedback where water starts to evaporate in the oceans. You know that happens. Water evaporates when it's hot. But water vapor itself is a greenhouse gas. So if that water vapor starts evaporating enough, then that reinforces the greenhouse effect, which makes it hotter on the surface, which makes more evaporation happen. And you can see where this is going, which makes it hotter, more evaporation, and there's nothing that can stop it once it gets beyond a certain point. And literally the oceans boil off, and all the hydrogen escapes into space, and you end up with a planet that's really hot and really dry. So we think that early on, Venus just had too much sunlight, lost its oceans to a runaway greenhouse, and then once it's an irreversible change. You can't get the water back, and once it's that hot, all the atmosphere is CO2, and so it's this self-reinforcing. It's pegged basically in the red zone. It's just a really it's an end state of what can happen when an Earth-like planet gets a little too much sunlight.
So we probably suspected something about that before Venus Express. So what was it that Venus Express was tailored to study, and what did we learn from it?
Yeah, I mean, we had sort of a cartoon version of that from previous spacecraft, but we had a lot of detailed questions about what is the atmosphere really made out of, and what is really happening in the atmosphere when sunlight interacts and forces the dynamics, it forces the atmosphere around, and what's happening with the winds and the clouds. So we really got this whole much more detailed picture of what's going on in the clouds and the atmosphere with the motions and basically the weather of Venus. And you know, so I could tick off a few discoveries that we did make, but more even than just like sort of big aha discoveries, it's more that complete picture of the motions and the structure of the atmosphere, which allows us to do a much better job of plugging into our climate models. Just like we have climate models on Earth, which now have become so important in all these questions about the way our planet's changing, we have climate models for Venus too. But in order to have a good model, you need good data. And before this mission, we really didn't. You know, so some of the specific discoveries we made were, well, for one thing, lightning. We had suspected there was lightning on Venus, but we actually detected it really strongly with Venus Express. Not by seeing it with the cameras, but by hearing it with the magnetometer. You know how with your radio, you're driving along and there's a thunderstorm and there's lightning and you get this this crackling sound? We got static, basically that signal really clearly of lightning on Venus. And then we discovered some other, you know, pretty weird stuff. The poles of Venus, there are these, you've heard about the polar vortex on Earth, which sometimes gives us nasty weather. Well, picture the polar vortex on steroids, where there are these basically, it's like a permanent upside down tornado, but it turns out sometimes there are 2 of them or 3 of them rotating around each other, and it's this sort of weird dancing set of these chaotically moving, they're basically like upside down tornadoes, upside down because the air is like rushing down, but dancing around the poles. And those are just really beautiful and dynamic structures. So, you know, we learned a lot and we saw a lot with this mission.
Now, David, I know we have a slide or two that includes that vortex. So maybe we could go to the slides and you could tell us a little bit speak to the slides, and then we'll come back, ask you a few more questions, and then have the audience ask you some questions. So if we can go over to the slides, and oh, slides in the corner there. I think
well, there's our little spacecraft.
Perfect. Okay.
There's our little spacecraft. You can see its solar panels. Obviously, this is an artist's conception. We didn't have another spacecraft out there to take its picture. But you can see it's really quite simple. It's the size of, you know, a sort of a washing machine, and has solar panels and a number of instruments, and basically the radio antenna. It was on a 24-hour orbit. So every 24 hours, once a day, it would, when Spain was facing Venus, it would turn away from Venus towards Earth and point that antenna and communicate with the radio antenna in Spain and send back what it had learned every day.
Terrific.
And this is just one of, you know, literally many, many thousands of images showing you on approach to Venus with Venus Express. And you see these sort of those sort of dark rippling features in the atmosphere. That's a lot of what we were studying. Those are the cloud tops. And it turns out to be chemically really weird and complex and interesting. There is sulfur dioxide on top of the clouds, which is varying over time. And we made some really strange discoveries of sulfur dioxide. We think it's probably connected with volcanoes on the surface. And so those colorful markings move around over time. And a lot of what we were doing was sort of tracing those markings, you know, like an ink blot in water, to follow the atmospheric motions and really understand what sunlight is doing to the atmosphere of Venus. And here's a series of images. These are actually composites. So on the left, those sort of bluish images, that's the daytime atmosphere. And then on the right, those orangey images are the night side atmosphere. And one thing we could do with a spacecraft that was really cool was with the night side, we could peer down into the atmosphere in the infrared. And those markings are, you're seeing features at different levels in the cloud. So not just the cloud surfaces, but it's almost like, you know, an X-ray. We can see down into the clouds at different infrared wavelengths and get this sort of 3D picture of the motions. And so we're showing you here 6 different spheres, you know, just 6 different times to get a sense of the variability. And we could watch these features and watch the atmosphere rotate around. It's what we call the super rotation, where the atmosphere whips around much faster than the solid rotation of the planet. And it turns out that it's doing this at different speeds at different altitudes. So this allowed us to get a 3D or even a 4D, if you want to use the time, add in the time dimension, picture of the clouds. And these are just some snapshots showing some of that analysis we were able to do.
In that super rotation, can you say, how does that compare to Earth? Because we're used to our breezes and windy days here. What is it like compared to Earth?
It's pretty intense compared to Earth. We're talking about, you know, well over 100 miles per hour all the time, the upper atmosphere sort of whipping around the planet. This is at cloud level, which is, you know, 30 miles up. Down on the down near the surface, the winds are quite gentle, just you know, maybe like 1 or 2 miles per hour. But remember, the atmosphere is almost 100 times as thick as Earth's atmosphere. So even a gentle wind like that could knock you over because the atmosphere is so thick. So the force is great.
What's that?
Okay, so this is not a Venus Express image. This is a Magellan image. Magellan was the spacecraft, the last American spacecraft at Venus, which was, you know, sort of sadly, well over a decade ago. Yet it was an amazing mission. It was a radar mapper, and so this is a radar image of the surface of Venus. And this is just one of literally thousands of volcanic features on Venus. This is we call the tick for hopefully obvious reasons. It looks sort of like a tick, but what it really is a volcano that's kind of collapsed and has these faults, these tectonic faults radiating out from it that gives it that tick-like structure. And I just wanted to include this to give a sense of the diversity of the surface features on Venus and the extent to which they're dominated by volcanic features. Venus is a planet with a volcanically active past. And one of the big mysteries, one of the things we wanted to try to help address with this spacecraft is the big question of whether or not Venus is still volcanically active. That would be really fascinating to know because we don't know of any other, well, okay, there's Jupiter's moon Io, which is this weird tidally heated moon, which is volcanically active. But we don't know of any other rocky Earth-like planet that is active today. Mars died out a long time ago. And so it would be so neat to be able to monitor active volcanism on a nearby world. And we suspect that Venus has active volcanoes. And when we see images like this from Magellan, we know that there are all these volcanoes, but are they all extinct? So this is sort of setting up for the next data set from Venus Express. I think there's one more that image that just shows you the actual, this is that same feature. This is what the actual Magellan data looks like. That first one was colorized, which is sort of a cheap trick, except for we think those are the actual colors that you would see on Venus because the atmosphere is very sort of reddish. because of the depth of the atmosphere with all the light filtering through. But this is just a slightly wider image showing you one of these strange volcanic features on the surface.
With
but
the
now
secret CIA headquarters there?
Yeah, that's right. That's classified, that little square. Yeah. But if you could go to that next image, it shows you some data from Venus Express. There we are. And this was actually really cool. Venus Express is an orbiter, and with all those thick clouds, you would think you wouldn't be able to see the surface at all. But we discovered that there's this one, what we call an infrared window, one narrow wavelength around 1 micron, which is just a little bit redder than red, a little bit farther out on the spectrum towards the infrared. And just at that one little window wavelength, there's enough of the radiation gets through so that you actually can see the surface directly. So we made maps of the temperature of the surface from Venus Express, and this shows you one of those temperature maps. And then where the red is hot and the blue is cooler, and the thing that dominates this temperature map is the topography, the mountains. You know, at the top of the mountains it's cooler, and down lower in the basins it's hotter. But what we were able to do, which was really cool, was, so to speak, was compare this map to the expected temperature map just from the topography. We knew the topography from Magellan, and in some places there were anomalies. In other words, there were places where the surface was a little bit hotter than it should have been, or was radiating a little bit more than it should have been. Huh. And by correlating the geography of those hot spots with where some of the recent-looking volcanoes are, we think we've been able to show that, in fact, there is evidence of active volcanism on Venus. And this was one of the big results from this spacecraft. I wouldn't say we've 100% proved it, but we have evidence now that does point in the direction where some of the areas around these giant volcanoes seem to be younger and seem to be radiating more. So we think we're on the trail of detecting active volcanism on Venus, and it's one of the reasons I really want to go back with future missions to verify this, and if there are active volcanoes, to be able to study them and compare them to the volcanism we have on Earth.
Fantastic. Now this, I think, is the vortex you were talking about.
Yes, yes, thank you. This is an image of that polar vortex, and it's just, you know, it's this strangely shifting structure that, so what you're seeing, where it's brighter, you're seeing deeper, actually, so it's hotter in the infrared. So you're actually looking down right on the pole here, and you can see you can see down deeper right in the center, because you're basically looking, it's like you're looking down a giant funnel closer to the surface. And this thing is constantly shifting and swirling around, and it's just, like I said, it's this sort of giant, permanent, upside-down tornado that resides around the pole of Venus. So
we have a movie of it, but before I go, I just want to say it looks like a George O'Keeffe painting to me. I don't know if that's for anybody else. Here is what you were talking about, David.
Oh, there you go. Great, great. Yeah, so again, you can see this thing sort of shifting and swirling around, and every time we looked at it, it was a little bit different. Sometimes it split into 2 or split into 3 and then merged again. And when you consider that you're looking over you know, a diameter of probably about 1,000 miles here, this is a really large and sort of ferociously dynamic structure.
Oh, we can go back to David, because that's the last slide. Why doesn't Earth have one of those?
Well, Earth does have a polar vortex, actually. It's just much more muted because the dynamics of Earth's atmosphere are not as intense. We don't have anything like the super rotation. You know, what's really happening on Venus is you have this super rotation where the atmosphere is whipping around. And then you also have what we call a Hadley circulation, which is air that's rising at the equator and sinking at the poles. And Earth has that Hadley circulation too. We have that rising at the equator and sinking at the poles. But if you think of it, when that superrotation sort of runs into that Hadley circulation at the poles, you know, it's like the water draining in your bathtub or something, it's got to go somewhere. And as it approaches the pole, it's rotating faster and faster and sort of sinking down. So it's just the combination of all those different dynamical factors leads to that kind of dramatic behavior.
One last question. Well, one last question about this mission from me, and that is, were there any surprises? Anything that was like, what is that?
Yeah, there were a lot of surprises. The biggest surprise to me will sound a little bit sort of nerdy and obscure, but it's a really weird one. So one of the things one of the signatures we have on Venus that tells us that a lot of water escaped, as I was describing earlier, is that there's a huge amount of heavy hydrogen on Venus, deuterium, which is a deuterium atom is a hydrogen atom with an extra neutron. And when hydrogen is escaping from an atmosphere, it leaves behind the deuterium because it's heavier, it doesn't escape as easily. So one of the things we've known for a while about Venus is it has a really huge deuterium to hydrogen ratio, 100 times Earth's deuterium to hydrogen ratio. And that tells us that most of the hydrogen escaped at some point. All the light hydrogen left and left behind the heavy hydrogen. So whenever a lot of something is escaped, it leaves behind the heavy stuff. So you can tell there used to be a lot more of it when you see all that heavy. I hope this is making sense. Yeah. So that deuterium to hydrogen ratio on Venus is huge. We knew that from an earlier spacecraft. But with Venus Express, we were able to measure it in more detail at different altitudes. And we discovered something that doesn't make any sense. I still don't understand it, which is that high up in the atmosphere, this deuterium to hydrogen ratio shoots up. There's a lot more deuterium in the upper atmosphere than there is in the lower atmosphere. And this doesn't fit our pictures, our models. It should be well mixed. It should be the same. So there's something going on there that we don't understand. And you know, so it's sort of another mystery that we have to send another spacecraft to go back and study. So that was a big surprise. I would say the amount of lightning was a surprise. I mean, some people thought there would be lightning, some people thought there wasn't, but there were sort of constant, really intense lightning flashes going on. And that's also, by the way, strange, because from what we understand about how you make lightning based on Earth, you need rainfall and droplets to make lightning. You're separating the charges on those droplets, and then you get the electrons are distributed in such a way that you build up a charge and you have a lightning flash. On Venus, we don't have that kind of rainfall. So there's something generating the lightning, but we don't know what it is. Huh. So every time we make a discovery like that, we have just more questions, and we need to argue for more missions to go back and figure out what it is that we now know that we don't understand.
That will be my last question, but before I ask my question, I thought we might open it to the audience to have their questions, and there are many hands up, so we'll just work our way through.